All right, we are right on time. Laszlo, you can get started. Thank you.
All right, thank you. So this is the Wheelhouse of Horrors. This is a talk about the perils of building Python extension wheels. My name is Laszlo Kollar. I work at Bloomberg and the Python infrastructure team. We, as Bloomberg, we have about 8,000 engineers in total, and about half of them actively use Python. My team supports these active sort of 4,000 Python users with Python tools. We own a few libraries and workflows. And one of the areas we handle in Python infrastructure is the Python packaging realm. I'm also an occasional maintainer and contributor to the Audit, Will, and Linux open source projects. And through these projects and in my work as well, I've come across a lot of interesting problems in the packaging space, particularly when it comes to building extensions. And in this talk, I wanted to bring you a few of the, I think, more interesting examples. And because these extension wheels, building these can be particularly challenging, and they have definitely some very interesting aspects, which are non-trivial and can be really, really difficult to debug and troubleshoot. I felt like in a talk like this, it would be good to showcase the sort of the common problems. And because the Python community has developed tools and specifications to help users and maintainers avoid these mistakes, I'm going to talk about those specifications and tools. Before we dive into any of these examples and sort of the problems, let's cover some ground and talk about Python wheels first. Who here knows what the Python wheel is? Okay, I guess that's about half of the audience. So let's definitely cover in more details what Python wheels are. They are not cheeses of wheels, definitely not. They are pre-built Python packages. What they do is they're basically just a zip file with this special WHL extension, and they contain generally Python code, metadata, and compiled code as well, potentially, like Python extensions. The main advantage of these Python wheels are that they are pre-compiled. They are pre-built, so when you install them, you don't have to perform another installation step, another build step, which means that installation becomes much faster and simpler, and it's also more secure. There are two flavors of wheels. There are pure Python wheels, which, as the name suggests, contain Python code, but there can be other things inside. They can also contain data files and metadata which describes what's inside that wheel. Platform wheels, on the other hand, they contain the same things, they can contain the same things, but they can also contain native libraries. They're native because they're native to the platform, and they tend to be compiled code, so written in C, C++, or some other compiled language. And we can also split these into two subcategories. There are native extensions, which are Python modules written in a different language. Years ago, when I was new to Python, this blew my mind. The fact that you can write C or C++ code, compile it, and then actually just import that into Python like it was an actual Python module, because that's effectively what you're building. These are native extensions. Beside these native extensions, these wheels can also contain library dependencies. Again, these are native libraries, and they tend to contain, they're general purpose libraries, and they contain usually functionality which is required by our extension, but they have nothing to do necessarily with Python. Let's look at the contents of a wheel just to see how these look like. So this here is a pure Python wheel, and this is the very popular Flask project. It's a pretty simple wheel, and you can see here we have Python files up there, and we have some metadata. Pretty simple stuff. Now, when it comes to platform wheels, they are somewhat more complicated. So again, we have Python files. I'm not sure how well the colors are visible on the projector, but down there we see a bunch of Python files. Then we have, again, metadata. But now we also have an extension here. And that extension, as you can see from the name, that is built specifically for this CPython version 3.11. Linux 64-bit. This is what makes it a platform wheel. It's specific to that platform. And then we can also see up there a few, oops, sorry. Up there, we can also see a few other files which are, again, native libraries, not extensions in this case. Those are math libraries, which are required by NumPy, some functionality in NumPy. And they are written in C, and they are required for extensions in NumPy to function. You can see that there's something weird going on with the file names, and we're going to come back to that and understand what exactly, why exactly those numbers are there. Now, let's look at the file name, because the file name is very interesting, especially for platform wheels. They contain a lot of useful information. And you can see it's quite long. There's a lot of information encoded in it. So if we zoom in a little bit, we can see this is the full file name. The file name is standardized, so all wheel file names should be following the wheel standard. PAP 425 standardizes this, and basically the file name contains wheel tags. These wheel tags are separated by hyphens, and if we take this file name and we just split it up based on the hyphens, we get the following tags. And we can associate these with the corresponding wheel tag names. And now I think it becomes much simpler to understand what this file name contains. So we have, if we go one by one, we have the distribution, which is just a fancier way of saying the name of the package. That's NumPy. We have the version. Then we have the Python and the ABI tag. And these basically define what version of Python this wheel was built against and what it will work with. And in this case, this will only work with CPython 3.11. And now we come to the platform tag. And I think the platform tag is the most important for this talk. You can see that it mentions many Linux a few times, and it has a lot of information encoded in it. If we zoom in a little bit and try to understand what the platform tag is, it was invented back when wheels were a new thing as a means to encode what platform this wheel is compatible with. And in the good old days, this was pretty simple. You would have something like Linux 64-bit or Windows 32-bit. And this works really well for platforms like Windows or macOS, where you can say that I'm going to build this wheel for a specific version of macOS, and because those major versions of the operating system tend to be pretty stable, and they tend to be forward compatible or backwards compatible, if you build a wheel for that platform, you can be sure that it's going to work on that and the following versions of the OS. But that is not the case for Linux. Linux doesn't really have the concept of a single sort of OS. It's just lots and lots of distributions. So if you say something like Linux 64-bit, then that would potentially mean that Ubuntu 16.04 would have to be supported by this wheel just as well as the latest rolling version of Arch Linux from this year. And those two would be wildly different in terms of the supported contained libraries, kernel, and many other aspects. Because of this, the community came up with the concept of the Many Linux standard. And what Many Linux means is a pseudo distribution or a pseudo OS, basically, which means that if you have a Many Linux distribution, a Many Linux compliant distribution, then you can know that all of the wheels which are Many Linux compliant will work fine on that particular OS. And here I listed 3 of them. The first 3, Many Linux 1, 2010, and 2014. And the naming scheme has changed slightly since then, but these 3 were the first 3 ones. You can see here the PAP, the first PAP, which introduced the Many Linux 1, and there are corresponding PAPs for later versions of Many Linux as well. And this is the point where we arrive to understanding what the Many Linux policy is and actually looking at those horrific examples of what happens if someone were to not follow these standards and why it's important to lay down the foundation and these standards. So we're going to go through one by one and try to understand what these points mean. And these are the same basically for all of the Many Linux standards. I just took the Many Linux 1 as the example here. And when we look at these, I'm going to showcase examples. And these examples are from real-world wheels, which exist probably as of today on PyPI. They are probably still up there. But to protect the innocent, I removed the names, so you won't see that. But there's a very good chance that if you wanted to, you could actually download these and see for yourself how they break and how they don't work, as you would expect. Okay, so starting with the first one, what the Benelux standard says is that wheels should depend only on an extremely limited set of external shared libraries. And I think we could phrase this sentence slightly differently to make it easier to understand. What this is actually saying that wheels should not depend on any external shared libraries except for a few, a limited set. And why is that? So to understand why wheels should not depend on external dependencies, let's look at one which does depend on external dependencies. So this is our first example. We install our unnamed wheel from PyPI. When we install it, we get a very nice sort of Benelux 1, Benelux 212 tagged wheel. This shows us that this is a fairly well built and tagged wheel. So we install it, everything's good, and then we try to import it and call a function in it, and it just blows up with this error message which says that cannot open shared object file, no such file directory, and then you get a helpful link to the documentation talking about something called LD library path. And I think if you're a Python developer, you at this point might have no idea what any of this means. And you probably wanted to solve a problem, and now you have two problems to solve, so this is definitely not a great situation. Let's try to understand what's going on here. So we have our wheel, that's the big blue box there, and we have a few Python files in it. And when we import one of these Python files, in turn it triggers loading this extension, that Python extension, which again gets imported into our CPython interpreter. And that extension depends on an external library. That's our dependency at SO. And as you can see, that's outside of the box. It's outside of the box because it's not part of the wheel. And this means that if it's not part of the wheel, there's no guarantee that it will be present on the machine where we're trying to run this. And that's precisely what happens here. We don't have an external dependency installed. And this causes two issues. One is that now this complexity of finding the library and installing it is the user's problem. And that's not great for the user as a user experience. And the second problem is that even if you were to find and install that library, which you might actually not be able to, maybe you don't even have root access on that machine. But if you're able to, there's no guarantee that you're going to install the exact version of that library which the Python wheel was built against. And maybe they would not be compatible, which is a more subtle but just as dangerous problem to have. So how can we solve this? The solution is pretty simple. We can just take this external dependency, and when we build the wheel, we just move it inside the wheel. And this solves both problems, because now when you install the wheel, you're always going to be guaranteed to have the external dependency present, and you will also be guaranteed to have the exact right version available. But there is always a but. This is not quite done. There is still something else here. And here is another example wheel. This is a different wheel which actually tried to do the right thing, and they copied all of the external dependencies into the wheel. They did something weird here because what you see here as a file listing, these are all duplicate files. They should be symbolic links. If you know library versioning on Linux or on Unix system how it works, usually you have something like libkrb5 so3, which would be a symlink to libkrb5 so3.3, and that's how they can version minor versions and expose it as the major 3 version. None of this really matters, but this is one problem with this wheel. And the other problem is that because of the way the dynamic loader works on Linux, there are no namespaces. If any of your library dependencies requires something like libkrb5 so.3, and let's say that you have 100 different dependencies, you have a very big application, and any of the other libraries you're using also happens to require that libkrb5 5so.3, then the loader on Linux will say that, oh, I've already loaded this, I have it, and it will not load the next one, the other one. It will just give you the exact same version, which might not be compatible with the other extension. And because of this, it's possible that these are ABI incompatible, and what can happen is that you get a runtime crash when you load it, and these kind of problems are extremely difficult to track down. You basically just get a segmentation fault, if you're lucky, or you might get bad data. So it's actually not that hard to solve this problem. Based on our previous solution, what we can do is we take our dependency and we just make it unique. So basically we put some sort of hash or some unique number into the file name, and then we just have to update all of the extensions which reference this to reference the unique version. And this means that from this point on, our wheel will have its unique dependency of this external dependency, and no one else should be depending on it, which means that we can have multiple different dependencies in our application, and they will all nicely coexist together. And going back to a previous slide, now we can see and understand why exactly NumPy is doing this, and they are doing the right thing. They copy the external dependencies into the wheel, and they make them unique by changing the file names, by adding a hash. And this guarantees that NumPy will work correctly, even if your application happens to depend somewhere else on lib4tran.so, for example. Okay, so now we should have a better sense of why Many Linux says that wheels should not depend on external dependencies, but it does say that some of them are okay, a limited set. And that is actually listed in the Many Linux spec, and this changes across Many Linux versions. These libraries are okay to depend on, and the reason why that's okay is because these libraries are pretty much every single time on all distributions are shipped with the distribution, and they have very stable ABIs, so they are not going to put your extension at risk of not being there or being in a slightly different ABI version. Okay, so now we handle the first one. Let's move on to the second rule here. Python wheels should depend only on old symbol versions in those external shell libraries. Okay, so let's look at our next example to understand what these old symbol versions mean. This here is an incorrectly tagged wheel. We are running a very old version of Red Hat Linux. I think it's been end of life for quite a while. But for this example, just to demonstrate the situation, let's use this rel 6 or CentOS 6. We install our extension with Python 3.9, and then we get a Many Linux 1 tagged wheel, which sounds good. And then we try to import it, and we get this enormous stack trace. I had to actually truncate it to fit on the slide. And at the very end of this error message, we see this sentence saying libc SO6 version glibc 2.14 not found, and some more text. I think similarly, if even not more cryptic as the previous one, I think this might be really hard to actually understand. What does it try to say? So to understand what this error message is trying to say, we need to look at what Many Linux actually means in terms of the glibc version. glibc is the GNU standard C library, and every single Many Linux version tends to depend on one specific version of libc. And this means that our extension can use that particular version of libc, and that also means that it will be backwards compatible on new versions to that libc. So, and you can see that CentOS 5 was at libc 2.5, and CentOS 7 is at 2.17. And actually, later versions of Many Linux changed slightly different. They made this a bit more dynamic. So now Many Linux actually depends on a specific version of the glibc version. And that's part of the naming. So you see XY, that is now the version of glibc. And with that, we can actually create aliases to the older Many Linux versions, and now we can say they are basically equivalent. Many Linux 1 is basically Many Linux 2.5 because that's the glibc version we need. And what this means is that our extension and anything in that extension can depend on functionality up to glibc 2.5. And knowing this, if we get this handy tool out called audit wheel, we can take a look at what glibc version this is actually trying to use. So we feed it this badly built wheel, and you will see there that it actually highlights that this is using glibc 2.14, which actually we don't actually have to understand that, because it will tell us down here that the actual Menelux tag version, what this wheel should have, is 2.17, and not Menelux 1 as it states. So for some reason, the maintainers of this this wheel sort of understood that Menelux is a thing, but instead of applying it correctly, they just sort of hard-coded it in the file name, which is not correct. And here we can see that Menelux 2.17 indeed is actually CentOS 7 as the first version of the distribution where you can use this. And of course, it doesn't mean that you can only use it in CentOS 7. You can use it in any distribution which ships at least glibc 2.17. So now, with this, it should make it a bit easier to understand what it means that these wheels should only depend on old symbol versions. So it has to be at least that old, and there are other libraries besides glibc, but we can more and more focus on just glibc as the minimum version those wheels have to satisfy to be Menelux compliant. And the last thing here, we actually can just completely skip that, because it says that they should only depend on a widely compatible kernel ABI, but the Linux kernel in practice is so stable that this is never an issue, so we can pretty much just ignore it. Okay, so to sum all this up, what we've learned so far, if we want to build a wheel, an extension wheel which works everywhere, we have to minimize the external shared library dependencies, and for this, we should vendor them into the wheel, meaning we have to copy them inside the wheel and then make them unique to the extensions. We also need to depend only on old symbol versions, and this means that the wheel can only depend on the lowest version of the distribution what we want to support. And then we also have to apply the correct wheel tags to actually express that what Menelux versions or wheel is compatible with. And this seems like an awful lot of work for any library maintainer to go through and do manually. So are there any tools? Yes, there are tools available. And I'm going to showcase the most important ones, or at least what I think are the most important ones. So the first one is Audit Wheel, which is a PyPA project. And we've already seen this. It can show you Menelux compliance. That's just one thing it can do, and that can be useful to inspect the wheel when you encounter an issue, similar to what we've seen. But something much more useful it can do is it can repair wheels. So it can basically do the vendor external dependencies and then make them unique to the wheel. And besides this, it will also adjust the wheel tags correctly. So you don't have to basically worry about any of this. As soon as you build a wheel, you can just run it through Audit Wheel, and it will basically make it Menelux compliant. And you can see here in the example, I actually fed it in the incorrectly tagged Menelux 1 wheel, and out came a correctly tagged Menelux 2.17 wheel, correctly tagged. Now, this is not enough, because you still need a build environment where you can ensure that when you build your Menelux wheel, it actually has the correct build tools and the correct libraries it can depend on. And for that, the PyPA also maintains this set of container images called Menelux. These are images, one image per Menelux standard, basically, and per architecture. And this is not the full list. There are actually many more. If you use one of these, for example, if you want to be Menelux 1 compliant, you can just take the Menelux 1 image. Actually, do not try to be Menelux 1 compliant, because it's very, very old. But if you want to be Menelux 2014 compliant, for example, you can just take that image, build your wheel inside that, and that will ensure that you are using the right dependencies and the right build tools. And finally, we have CI build wheel, which takes all of these tools I've mentioned, and it bundles them into this nice package where you get tools in different CI systems like GitHub Actions or Azure pipelines, and it will do everything for you basically auto-magically. It will use the Menelux or similar images for the muscle standard. It also does this on all the other major operating systems, so macOS and Windows. And it also will call audit wheel to make sure that these wheels are correctly vendored and tagged. And you can see here a matrix of the different environments and Python versions supported. I think it's quite extraordinary. It's basically, it's almost too big to fit in a single slide. All of the Python versions, all of the OSs which matter, basically. And to sum all this whole talk up, I guess we can say that building platform wheels is complicated. And if you want to take just one thing away from this talk, it would be, for me, is that everyone should just adopt CI build wheel, because it's going to make everyone's lives much, much easier. Thank you.
We still have 5 minutes. Anybody have any questions?
First of all, it was really amazing talk. I faced so many of these errors, but never understood the real reason. I understood that, okay, the LD Python thing, and I think most of them. I think if you have played along with a lot of pip, you have faced these errors. However, I still face these errors, especially if you go with the GPU libraries, right? And you mentioned that if we take that SO file inside the pip, inside the wheel, it's fine. But do you think there's a chance of bloat? Because if you do a lot of libraries, things might break. And adding to that question, when do you think it is bloat, and when do you think we need to stop that?
Did you mention GPU wheels?
Yes.
Okay. So that's correctly. I think it's a really interesting point you're making, because I think this sort of bloat started to become a really significant issue with these sort of GPU-specific wheels, where some of these wheels can be hundreds of megabytes large just because of all the external dependencies. It is a real problem, and there isn't a great solution to this at the moment. The Python community has been discussing this for a long time. And I think very recently, I think on PyCon US this year, NVIDIA actually announced that they are working with the community on actually better standardizing this. One of the problems here is that there are wheel tags and there are Menelux tags, but none of those actually account for platforms when it comes to specific GPUs. So if you want to publish a wheel just for CPUs or just for NVIDIA GPUs, you cannot really do that today. And that means that you can either bloat your wheel too much by putting all of the potentially supported components into that, or you have to distribute it somewhere else separately, and you have to provide more steps to the user. So to answer your question, there isn't a great solution to this, and yes, that bloat is definitely, it's real.
Adding one more point, what are your opinions on Anaconda? Because it helps to manage some of the packages. Do you think any regularization wherein some Python wheels, like alongside some tools which help us manage, common points, that might help? I don't know if things like that exist.
I think Anaconda is great. The trade-off is that, and I think the power of Anaconda and the Conda ecosystem relies partly in the fact that it can manage system dependencies, external dependencies. So in the Conda ecosystem, you can say that I also depend on this non-Python dependency. I don't think that will ever come to the sort of native Python tooling, just because there's so many aspects of that which are not relevant for Python. But I don't know. I think there's a lot to learn from that ecosystem, but I don't think it's going to be the solution for something like pip, for example.
Yeah, thank you, thank you.
Thank you for your talk and your work in audit wheel and stuff. So I'm just wondering, in the newer many Linux specifications, you only tag the libc version. So how do newer specifications decide what version of each library to allow for wheels?
That's a really good question, yeah. So basically, the perennial Linux standard, PEP 600, which introduced the notion of now we actually only look at the glibc version, it turned things around, and it said that we're going to look at glibc and assume that whatever most the Linux distributions tend to ship is going to be the minimum set, and it's not a fixed list anymore. I think, in effect, this mostly means that you don't vendor most libraries, and as we are building new Linux images, and there aren't now sort of fixed list of dependencies, we do more testing. So when there's a new Linux standard, we can test wheels built against a new standard, a new glibc on a few common distros, and basically see what are the common denominators, what are those libraries which are present there. So it's a more dynamic thing, and more like a living thing where we actually end up with many more Linux tags, and glibc becomes the only common thing. I guess one thing we could actually consider doing is saying that glibc is the only thing we're not going to vendor into the wheels at that point.
That's what sort of goes back to
the bloat. Yeah, that's true.
Any more questions? If there are no further questions, we'll wrap it up here. And thank you so much once again, Laszlo, for sharing your insightful thoughts with everyone. Really appreciate it. Please give him a big round of applause.